All right, let's talk about something you think you know inside and out. Area. It seems so simple, right? But its real story is this incredible journey full of ancient puzzles, a little bit of mathematical magic, and even a quest for the perfect shape. So quick question for you. If I asked you right now to measure the space inside a shape, what's the first thing that pops into your head? For pretty much all of us, it's some formula we memorized back in school, probably length times width.
And yeah, for a square or a rectangle, that feels like problem solved. It's obvious.
But what if I told you that this obvious answer is really just the first chapter in a story that spans thousands of years? We're talking about a tale of ancient Greek genius, a mind-blowing formula hidden in plain sight, and a search for the most efficient shape in the entire universe. So let's start at the very beginning.
Okay, first things first. Let's just make sure we're on the same page. What do we actually mean when we say area?
At its most basic, area is just the amount of flat space a shape covers. And we measure it by seeing how many little 1x1 squares we can fit inside it. For a rectangle, this is super easy. The squares fit in there perfectly, no gaps, no overlaps. And that's exactly why length times width works like a charm.
But the second we introduce a curve, our nice, simple method just completely falls apart. And this brings us to the big challenge in the story of area, the problem with circles.
And right here, this is the heart of it. With a rectangle, our little square units pack in perfectly, like tiles on a floor. But you try to do that with a circle? Ugh, it's a total mess. You've got all these awkward little gaps and bits of squares hanging over the edge. So how in the world are you supposed to get an exact measurement when your measuring tool just doesn't fit the shape?
Well, the ancient Greeks ran into this exact same problem, and they came up with a solution that was just genius. They figured, instead of trying to force squares into a circle, what if we could turn the circle into something we already know how to measure?
This is just so clever. Picture it. You slice a circle like a pizza. Then you lay the slices out, alternating tip to base. The more slices you make, the flatter those bumpy top and bottom edges get. And if you could imagine making an infinite number of tiny, tiny slices, you'd end up with a perfect rectangle. The height of that rectangle is just the circle's radius, and the base is half the circumference. Suddenly, a really hard problem becomes a simple multiplication. Amazing. But hang on, there's a little bit of a catch here, logically speaking. We can't actually use an infinite number of slices, can we? So our shape is always just an almost rectangle. Now this intuitive idea is beautiful, but for a mathematician, almost just doesn't cut it. They needed something more precise. And that tool was called the method of exhaustion. The idea is to basically trap the circle's area. You draw one polygon just inside the circle and another one just outside. Then you keep adding more and more sides to both polygons. As you do, you squeeze that space between them smaller and smaller and smaller until it basically disappears, zeroing in on the exact area. Now, if that sounds familiar, it should. It's actually one of the core ideas that, centuries later, would lead to the invention of calculus. So for hundreds of years, this complex ancient method was pretty much the best we could do. But then, way later in 1899, a mathematician named George Pick discovered a formula so simple and so surprising, it honestly feels like a magic trick. Take a look at this shape. It's this jagged, messy polygon, but all of its corners land perfectly on the points of a grid. Now, how would you find its area? I mean, you could try to chop it up into a bunch of triangles and rectangles, but man, that would be a nightmare. There has to be a better way, right?
Oh, there is. And it's called Pick's theorem. It is just gorgeous. It says that for any polygon like this, where the corners are on grid points, the area is simply the number of points on the inside plus half the number of points on the boundary minus 1. That's it. No complicated geometry, just count.
Okay, you ready? Let's try it with our shape. First, the interior points. Let's see, 1, 2, 3. Okay, there are 7 of them. So I is 7. Now, let's count the points right on the boundary line. And we've got 8 of those, so B is 8. Now we just plug those into the formula. 7 plus half of 8 minus 1. That's 7 plus 4, which is 11, minus 1, which is 10. The area of that crazy complicated shape is exactly 10. No cutting things up, no trigonometry, just counting. I mean, that is an absolutely incredible piece of math. So we have these amazing tools to measure area. But that leads us to an even deeper, more fundamental question. It's not just about measuring the area we have, but about how to get the most area possible.
Let's put it this way. Imagine you have a certain amount of fencing. Let's say 100 feet. That's your perimeter.
What shape should you make your fence to get the absolute biggest yard inside? Should it be a long, skinny rectangle, a perfect square, a pentagon? What's the most efficient shape?
Well, the answer is one of the oldest, most profound truths in all of geometry. For any given length of fence, the one shape that encloses the maximum possible area is always the circle. It is, quite simply, nature's most perfect and efficient container of space.
And this isn't just some abstract math idea. It's a principle that's woven into the very fabric of our physical world. I mean, just think about a soap bubble. The surface tension of the soap is always trying to pull it into the smallest possible surface area to hold the air inside. And that brings us to a final, beautiful question. Is this deep mathematical truth the very reason why bubbles are round?